Hi, we're Ether. We are seniors in computer science at CE Boulder, and we will be presenting our capstone project today.
Hi, I'm Eli. I'm the documentation lead.
I'm Matt. I'm the communications lead.
I'm Ifom. I'm the architecture lead.
I'm Kyle. I'm the backend lead.
I'm Alex. I'm part front-end lead, part version control lead.
I'm Jinxi. I'm graphics lead.
Hi, I'm Cassie. I'm the testing lead.
And I'm Josh Barber, product front-end lead, and our project sponsor is NASA and the Jet Propulsion Laboratory. Over the course of the school year, we have created software which we call Ether. Ether is an interactive 3D rendition of the solar system which runs inside your web browser. The motivation behind our project is to give NASA mission designers an easy way to visualize and compare the trajectories of different celestial bodies and spacecrafts. Therefore, Ether's core design is centered around flexibility and extensibility. When planning a new mission, like sending a rover to Mars, NASA must first decide when and how they're going to get there. Part of this process involves designing the trajectory the spacecraft will take as it travels from Earth to its intended destination. When dealt with this task, there are many factors one must consider. For one, the orbits of the planets and their alignments affect the launch date. It is better to launch during times where the Earth is closer to the intended target because it saves both the required fuel and time to reach the target. Furthermore, when a spacecraft arrives at its destination, the type of orbit or flyby impacts the science data that can be captured.
This is where Ether comes in handy. Mission designers at NASA can upload a new mission trajectory to Ether and visualize it in the context of the solar system with lightning speed. They can control the rate of time within the simulation and watch as the spacecraft transits from Earth orbit to a distant planet, moon, or asteroid. They can also compare two different trajectories at the same time, which is helpful in determining which one best suits their desired science objectives. While this is the motivation behind Ether, it is not restricted to visualizing future missions. It can also visualize the orbit of planets, moons, and asteroids and comets at any time in the past, present, or future. Similarly, the trajectories of spacecraft that were launched in the past can also be displayed and compared to missions of a different time. Aside from simulating the trajectories of objects in space, Ether also visualizes the size, shape, and rotation of the planets, moons, and select asteroids. We have designed Ether to be scientifically accurate wherever possible, but also accessible to a wide audience. We hope that our software will not only aid in the design of future space exploration missions, but also inform and inspire the next generation of space enthusiasts.
Ether's design is broken down into two main components, the front end and the back end. The front end consists of the web browser visualization written in JavaScript, HTML, and CSS, and it uses Node.js as a web server. The majority of the front end deals with the 3D visualization, which is all written in JavaScript. The Ether visualization is built on top of 3D.js, 3D computer graphics library, and API. 3JS was a perfect fit for Ether because it uses WebGL, which allows for the rendering of complex 3D animations in any compatible web browser without special hardware or plugins. Along with custom-built 3JS functions and objects, Ether also utilized the SpaceKit.js open source library to speed up development and aid in our understanding of 3JS. SpaceKit is a JavaScript library that aids in creation of 3JS scenes, cameras, and some objects specializing in space-related simulations. These two libraries, along with vast amounts of JavaScript, allow Ether to be an easily available application that anyone can use in their web browser.
The back end of Ether consists of a REST API which serves data to the front end for visualization. Examples of this information include XYZ position coordinates for each object at different times, parameters defining the rotation of a planet or moon, and physical constants such as mass and radius of celestial bodies. All of this data is obtained by the backend using an information system called SPICE. SPICE was created by the Navigation and Ancillary Information Facility, NAIF, under direction by NASA, to assist NASA scientists in planning and interpreting scientific observations from spaceborne instruments, and to assist NASA engineers involved in modeling, planning, and executing activities needed to conduct planetary exploration missions. Data for celestial bodies and spacecraft are loaded into the SPICE system via files called kernels. These kernels are produced by the most knowledgeable sources of such information, usually located at a mission operations center. For example, there are generic kernels that provide data on the planets, as well as specific kernels that provide data for a single spacecraft. The use of SPICE is part of what makes Ether so extensible. The backend comes preloaded with a set of kernels allowing users to visualize the trajectories of all the planets, most of the moons, and 300 asteroids. However, one can upload a new kernel to Ether and visualize the data inside it. NAIF provides a massive repository of kernels, giving users many options for customizing their simulation. In this way, the bounds of what trajectories a user can visualize are virtually limitless.
Our backend REST server is written in Python using Flask framework. Interaction with the SPICE subsystem is accomplished using the SpicePy package. The backend of Ether uses Docker to streamline installation and deployment. Using just a few commands, a user can build a container with all the codes, dependent libraries, and default SPICE kernels. The backend container can either be run locally or on the cloud, and is platform independent.
All right, and with that, we will get into a demo. All right, so when you load the app, you're brought to this little welcome page. Once you hit launch, it'll start to fetch data from the backend server for the current state of the solar system at the time you start the application. So everything's all loaded in here now. You can see the inner planets, Jupiter and Saturn over here, and the Sun. Up here at the top of the interface, you can see the current time of the simulation. So this is the time I started the simulation. So that's super useful to be able to keep track of where the simulation is at. Another thing you'll notice is this big grid that extends all the way through the solar system. This grid represents the ecliptic plane, which is the plane that's created by Earth's orbit around the Sun. One thing to note with this grid is each square is 1 astronomical unit squared, which is just a unit of distance that is equal to the average distance of the Earth from the Sun. So you can toggle this grid on and off if you'd like. Sometimes it can be kind of ugly, but other times it's useful to have on there. Another thing you can toggle on and off is this starry background. We put that in there so it looks a little nicer, but when JPL uses this, they likely will not have the stars on.
Alrighty, so I'm just gonna show you a little more of the simulation right now. I'll just toggle the stars off and turn the grid back on. And I am going to start the simulation. So you can see up the top the date is advancing now. And it's going at about 1 JD per second. So a quick note on JD, that's just Julian days. Basically you can think it's just 1 day per second. So yeah, we'll just zoom in here, and you can see that the history of where the body has been is represented by this trajectory tail. So I'm just going to go over here and increase it to 1,000. And again, this parameter is in JD. So you can see they got longer. But before they were kind of moving as the body moved, and now they're just fixed right there. And that's because the sim doesn't have 1,000 days worth of data yet. It's still fetching data as it's advancing. So once 1,000 days of data are in there, these tails once again will start moving along with the body. Another thing you'll notice is they are colored. So the color represents the speed of each body with respect to its minimum and maximum speeds. So Mercury is a good example of this. You'll see that it is red over here on this segment, and that is because over here it's a little bit closer to the Sun. So it's going a little bit faster when it's closer to the Sun because the influence of the Sun's gravity is higher, and then over here when it's a bit farther away, it's going slower. Now that's the same with all the planets that you can see right now. But you know, some bodies don't have a huge difference between their minimum and maximum speed. It's just important to note that the color gradient is on a per object basis. And the red speeds are the highest, these kind of beige yellow is lower, and the blue is the slowest. Yeah, here I'll just zoom out a bit and show you some of the other bodies in the solar system. You can see as we get farther out, we can see Jupiter and Saturn. Now, in the same length of time, they've completed a much smaller portion of their orbit. If we zoom out even more, you can see the planets Uranus, Neptune, and Pluto. The dwarf planet is way out here. Yeah, and I'll just zoom in to show you that it's hard to see these bodies, but they really are there. They do have a texture. So if we just zoom in here on Mercury, it's a little bit tricky. I'll pause it actually so that you can see it better. Yeah, so you can just barely see it right now. But yeah, there's its texture. Right now I'm going to zoom to Earth and just start it. You can see that Earth is rotating, the moon is going around it, and just a little more on this drop down. You'll see, once you expand it, you'll see all the bodies and like the satellites that they have. So Jupiter, these are just a few of the moons of Jupiter that we have loaded in right now. Similarly for Saturn. And I think I'm going to stop this here, and we are going to go on to the next bit of the demonstration.
Alright, so we're zoomed to Saturn now. Here, I'm going to show you the ability to get some information about the bodies in the simulation. So over here you can see its mass, and the planets actually are defined by multiple radii because they aren't perfectly spherical. So the two radii that we incorporate in our simulation is the equatorial radius right here, which is it just goes across the equator, obviously, and then the polar radius, which is the radius around the two poles. So you'll notice that the equatorial radius for Saturn is decently larger than that of its polar radius. And you can see that reflected in the simulation with how kind of squashed looking Saturn is. It doesn't look like a perfect sphere. It looks like a little squashed. Also on the information page you can see the time ranges, the valid time range for our data in the back end. Alright, so we're back in the default simulation. So I'm going to show the ability to add asteroids. We have about 300 asteroids and dwarf planets available from the back end. In this drop-down you'll see that these bodies are grayed out, and that just means that they're available from the back end, but they're not currently loaded into the simulation. So I'm going to add some of these dwarf planets and asteroids to the simulation. So every time I hit this plus button, it's just fetching more data from the back end for the body. Add a couple more. Like I said, there are a lot. There are about 300 available, so I'm not going to add them all in. But so yeah, and then I'll start this animation. So yeah, you can add a bunch of different asteroids in there. Another cool thing is the ability to adjust the rate at which time flows in the simulation. So using this slider you can either increase the rate of time or make it go in reverse. So you can kind of make things go quicker, go backwards. I usually like to keep it at 1 day per second because you can still see the animation, but things aren't too quick. So yeah, I think with that we'll go on to the next part. Alright, another cool feature of this app is the ability to create an entirely new simulation with respect to whatever body you want. So in this first field, you can type whatever body you want, and that's going to be the origin, the 000 point of the simulation. I'm going to go to Pluto's barycenter, which we'll explain a little bit more in a sec here. And we're going to see Pluto and its biggest moon, Charon. This third field here, yeah, I should have mentioned this middle field. You can put whatever bodies you want, provided they're available from the back end, all separated with a plus. And then in this bottom field here, you type in the starting date of the simulation that you'd like to see. So I'll hit create. I'm going to zoom in so we can actually see these guys because they're pretty tiny. One note is currently these bodies are their accurate radii as opposed to being 10 times that. So I'll start this animation and
yeah, so here you can kind of see that, like Eli was mentioning, the origin is actually Pluto's barycenter. Now, this is kind of one of the things we learned in working on this project, is that all the planets and all the bodies in the solar system, they don't orbit the center of mass of, like, the sun, for example, or, you know, the moon doesn't orbit the center of mass of the Earth. Everything actually orbits a barycenter, which is the center of like that system. So here we visualized Pluto's barycenter, and you can see that Pluto actually has its own orbit around its barycenter here. Similarly, its largest moon, Charon, orbits that same barycenter, and you can kind of see they're almost in this lockstep orbit. It's almost like a binary star system in that Pluto is pulled by Charon, and Charon is pulled by Pluto, creating this interesting pattern here, which we just thought it would be cool to show you, that our simulation can visualize that. Alrighty, so now we're back at the default sim, and I'm going to show you the compare functionality. So we click compare, it comes up with this page right here. I've already pre-entered some data into it, but it has similar defaults to the reset, similar formats. You've seen this before. And what this is going to do is it's going to create two simulations. There's going to be one on the left and one on the right, and they are going to be synced with both time and camera. So moving the camera on one does the same for the other simulation, and the times are the same, assuming that you start them at the same date. But the flow of time is the same, I should say. So I'm just going to create this. You'll see there's the Sun, Earth, and Mars with respect to the solar system barycenter. And then the second simulation has the same bodies with respect to Mars barycenter. And both starting times are the same, the 1st of May 2020. So yeah, it's fetching data from the back end, and my motivation for showing you this is there are a few different missions launching towards Mars from the Earth this summer. For example, NASA's Perseverance rover is going to be launching. And the reason that there's multiple missions that are launching to Mars this summer is because the orbits are aligned. So you can see that time is advancing now. Before it gets too far, I'm just going to talk about a few different things. You'll notice on the left here, the sun is in the middle because we made this simulation with respect to the solar system barycenter. And over here on the right, Mars is in the middle because we made this simulation with respect to Mars barycenter. So if we zoom in, we can see the sun, and Mars is very tiny, but we keep zooming and you can see it too. I'm going to zoom back out here and just pause it really quick. So it's June 7th, and I'm not 100% sure on this, but I think they launch around the July time frame. I should double check on that, but yeah, so you'll see here that the orbits are pretty close together. So let me make the tails a bit longer here. So you can see the Earth is approaching Mars. And let me just increase the rate of time really quick. Now, I've blown past the launch window, but I kind of just also wanted to show you the difference in how stuff looks when you create it with respect to a different object here, or a different center. So normally you can just see that Mars and the Earth are orbiting the Sun, but from Mars' perspective it looks like the Sun is orbiting it. And similarly, the Earth, since it's orbiting the Sun, looks different. It kind of draws out this interesting rose pattern. And you'll see here that these little loops kind of illustrate when the Earth is closest to Mars in their orbits. So these windows right here are where you want to launch to save the most fuel. It's best to launch in these windows. And yeah, with that, I think we'll keep going on to the next part of our demo.
All right, so the next feature we're going to demonstrate is the ability to upload a kernel from the front end to the back end. So Matt mentioned the JPL Spice repository of Spice data. So I'm just going to show how you can download some kernels from this website and visualize them inside of our software. So these are all kernels for satellites and spacecraft. So you can see there's a good amount. You can visualize quite a few things. So for this demonstration, I'm going to get the Voyager 1 and 2. So you see there are a couple different subdirectories when you look for a kernel. The SPK kernels are the ones that you can upload with our software. The SPK kernels contain ephemeris data, just basically the positions of the body over time. So I'm going to get this file for Voyager 1 and then this file for Voyager 2. So for now I'm just going to upload Voyager 1 and show you how that works. So you can use this upload button. You can browse for your file. That's the one we just downloaded. And then you can upload it. You'll get confirmation that it's been uploaded successfully. Otherwise you'll get an error in this little error log down here. So now that that's uploaded, if we hit the drop down, you can see that Voyager 1 is available from the back end, whereas before it was not. So I'm going to kind of show you the two main gravity assists that Voyager 1 took to get itself out of the solar system. Alright, so it's fetching data from that kernel we just uploaded. Alright, and just so we can kind of see the overall trajectory, I'm going to make the tail length a little bit bigger. Oops. And yeah, increase the rate of time so it doesn't take as long. So this is shortly after Voyager 1 launched from Earth, and we're going to show it slingshot around Jupiter and Saturn. So I'm going to increase the rate of time so we can see that a little better. So right here, that's the first gravity assist. You can see how drastic of a change in that trajectory it was. Right about now, we're going to get to the second gravity assist around Saturn. And again, you can see how drastic of a change in the trajectory it was. You can also kind of see how it's exiting the ecliptic plane and starting to go up in the, I don't know, I guess the plus Z direction, if you will. So yeah, and then I think next I'm going to show you a comparison of Voyager 1 and Voyager 2's flybys of Jupiter. So I already uploaded Voyager 1, so it's in the back end still. So I'm going to find the Voyager 2 kernel I downloaded earlier, and we will upload that, confirmation that it was successful. And now we're going to do another compare. So for this, I'm going to show you guys these flybys with respect to Jupiter's barycenter, so you can get a good feel of the different trajectories that the two spacecraft took around it. So on the left, we'll do Voyager 1. We'll start that on the 1st of January, 1978. And then on the right, we will show Voyager 2. So they did their flybys at slightly different times. So to make them kind of synced up, I'm going to start the simulation on the right a little bit later than the one on the left. All right, so we're fetching the data. All right, so we see our split screen view. Going to zoom into Jupiter a little bit so we can, I guess just see that it's there, rotating, doing its thing. So I'll zoom out so we can actually see their approaches, and then I'll zoom in once they get closer so we can compare. So yeah, I'm going to speed it up, and then zoom in as they get closer. So I didn't time the flybys exactly correctly, unfortunately, but that's all right. Still get the point across that you can compare these trajectories. One thing to note is how much more abrupt Voyager 1's trajectory around Jupiter is than Voyager 2's. Voyager 2 kind of took a little more gradual flyby, didn't get quite as much speed, but Voyager 1, on the other hand, was a lot quicker of a flyby. So we can kind of see this again. And a slightly different angle, and slow it down so you can see it a little better. So this is a very important feature to include in the software because it allows JPL engineers and mission planners to be able to visually compare different trajectories of like future missions that they're planning and kind of see exactly how they would work in real life. So yeah, get on to the next part.
Alrighty, so we're back at just the default sim here, paused. Really quick, we wish we could show more. We hope that this has been kind of a good overview of all the features that our application supports. Hope you can see that it's super flexible. You can add pretty much anything you want to it, and yeah, this demo's gotten pretty long, but we think all this stuff is cool, and we enjoyed showing it to you and building it this semester. So we just showed Voyager 1 and 2 and their flybys. So I thought it'd just be interesting to add these in and show you what they look like today. So that was back in the 70s and 80s, and you can see Voyager 1 and 2 are way out here. I'll turn off this stuff, and yeah, they're pretty far out. Yeah, so it's been great working on this project, and we're glad we got to show it off for you. So with that, we're going to switch back to the presentation. Thank you.
The process of developing Ether has been a thrilling experience for all of us involved. The opportunity to work with NASA JPL on this project has been more than we could hope for, and we're very satisfied with the results. We learned many lessons throughout the development of Ether that helped us reach the results we were looking for and will continue to help us in the future. We learned that constant communication and teamwork is essential to meeting deadlines with the expected deliverables. We also believe that splitting our team into two groups based on the two major project components was a great and important decision that helped us meeting all of the requirements of the application on time. However, this did amplify the importance of constant communication and collaboration between the two groups to avoid confusion and misinterpretation.
Focusing on the fundamental features rather than polishing the existing ones was also a key strategy that our team employed to develop the best application possible. We first began developing the key aspects to the simulation, then built on them to add more functionality. This allowed us to continue developing new features in order of importance without having to refactor code to add functionality that should have been there previously.
Some technical challenges we overcame was learning the Three.js library and applying it to our specific needs. Even though some of us knew JavaScript in advance, applying this knowledge to 3D graphics rendering is a whole new challenge. It was also challenging to find the kernels that contained useful information. Some information in the kernels required further calculation and modification before it would be useful in our application. This required a good understanding of units, coefficients, and equations related to astronomy.
Some of our toughest challenges were learning the languages and frameworks necessary to run the simulation correctly on every machine. Everything from HTML, JavaScript, Node, JS, SpaceKit.js, Docker, and Python were needed to develop this application. Each server had its own languages, packages, and instructions to run. Connecting all of the repository servers and languages was a tough challenge. Another big obstacle we dealt with throughout the project was a general lack of knowledge about the physics of the solar system. Being able to use SPICE data effectively requires a somewhat detailed understanding of celestial mechanics, and none of us were especially familiar with that going into this project. To mitigate this, we spent a lot of time during the planning phase dedicated to reading JPL documentation and information about planetary orbits, rotation, and shape, all of which allowed us to be better prepared for the implementation phase.
For me, the most difficult challenge was connecting everything every time we updated the code. Merging multiple branches in order to test and develop the code was tedious and challenging, but ultimately rewarding. However, despite that, I learned many different ways to code and run servers efficiently. I learned HTML, CSS, JavaScript, Docker, and much more from scratch, which will be very useful in my career as a computer scientist. I also gained invaluable experience working with a team on a complex programming endeavor that would have been unthinkable to do alone. I feel like we did a great job, and I look forward to sending the final project to NASA.
Through the whole project, I felt the communication skills are important, because with efficient communication, the project can be easier for group working. Another feeling is that the group team is more important than anything. I feel the experience this semester is going to follow the group flow, which makes everything clear and easy to work on. Thanks to our group mates, our awesome sponsor Muscle, our TA John, and Professor Allen.
This project involves using some libraries and languages that are not used on a regular basis, which is very interesting to learn about. I also reinforced my knowledge on HTML, CSS, JavaScript, and got a brief understanding of Docker, Three.js, and REST server. All of our team members and our sponsor is very responsible. He provided us with enough information and is very clear on the requirements. It was a very great experience in working with all of the team members, our sponsor Marcel, our TA John, and Professor Allen.
Thank you for watching, and we hoped you liked our project.